looking at Newton's laws, and we talked about Newton's first. What does Newton's first law of motion say? If you're accelerating, the forces can't be balanced. If you're not accelerating, the forces must be, I'm looking for a word that starts with letter B. I'm going to continue, but someone needs to get a headphone out of their ear first. Thank you. Okay. I told you about my car accident where it appeared that my ashtray full of pennies had shot backwards, but instead it stayed at rest and my car got pushed forwards when I got rear-ended. We showed you the magician tablecloth trick. We showed you a person on a subway. We showed you a space shuttle or space station reboost. We did a lot of thinking. Basically, we said, look, if you know an object isn't accelerating, which either means it's at rest or it's going at a straight line at a steady speed, that means you know forces are balanced. You can fill in some missing forces. We introduced the idea of a free body diagram to you. Then we got to Newton's second law. This is the equation. And this one, for my two that were away yesterday, now you want to start to pay attention. We said that the only equation you're going to get in this whole unit is F equals ma. Everybody, F equals what? F equals what? F equals what? It's on your sheet. Technically, you don't need to memorize it. You want to memorize it because you're going to be looking it up 100 jillion times. Okay? So we got to example 5. I want to show you some examples of where we can use F equals what? Okay. Space Shuttle has a mass of 2.03 times 10 to the 6 kilograms. That's correct. I looked up the specs for the Space Shuttle. If each engine can exert a force of 12.5, what the heck is, what's a capital M an abbrev for mega newtons? Ooh, Declan, what's A asking me to find? Acceleration. Look up, don't write this down. My first thought would be, well, maybe I'll go, don't write this down, A equals V. Do you see a VI or a VF or a T or a D? Okay, you're going to find, much as Einstein said, acceleration, Sarah Ashley, is a really, really important concept. And by the end of this year, you'll have a bunch of ways to find acceleration. Ooh, Declan, what are the units right there?
Kilogram.
Mass. Is there an equation that has mass and acceleration in it? Why?
Yeah.
F equals what?
F equals mass.
Get the A by itself, please.
A equals F.
Okay? Yet another equation. We'll call this Declan's theorem. He says that A equals F over M. All right. What's the mass in this question? 2.03 times 10 to the 6. That's okay. What's the force? Well, first of all, there's 2 engines, so we're going to multiply by 2. And then 12.5. You know what? The shortcut for mega, we could do a full conversion, write down what they gave you, and build the fraction. But Lily, the shortcut for mega is multiplied by 10 to the 6th. What's the acceleration on the space shuttle? So you want to get your calculators out, and you want all of you to try typing this in. You want to get your calculators out, and you want all of you to try typing this in. If I sense you're not, I'll start calling on you and damaging your self-esteem. I'm going to get my calculator out. More than one. I probably should put the top in brackets. I might get away without it, but I'm not sure. So times 10 to the 6th divided by 2.03. When I typed this in, by the way, I probably could have said there's a 10 to the 6th on the top and on the bottom in the same way. Do you see, what these, and the C's canceled. I think the 10 to the 6th will cancel because it's all multiplied. Did you all get 12.3? Units? It's an acceleration, Declan? Good. Declan, how many G's is that? How could I figure out how many G's that is? Can all of you on your calculator, can you go divide by 9.8? What do you get? How many G's? 1 point what?
1.26.
Wait a minute, Mr. Dewick. I read that astronauts are pulling like 5 or 6 or 7 G's. You told me you got these numbers from the website, from the NASA website, and we're getting 1.23, not 5 or 6. Mr. Dewick, is NASA lying to us? B, why does the maximum acceleration change as the engines burn? Why do the astronauts experience the maximum G's near the end of the flight, just before they shut off the engines, not the beginning of the flight? Riley. Speed and acceleration have nothing to do with each other. Acceleration will increase your speed, but acceleration and speed are different concepts. Just because you're going fast, just because you're going 100 kilometers per hour on the freeway, if you're going at a constant speed, what's your acceleration? 0. You won't even notice it. Good thought, but no. Why is it that the acceleration gets bigger and bigger and bigger and bigger and bigger and bigger and bigger? Joanna? Don't need to worry about any relativity or anything like that. Declan, what's your theorem?
Does it have something to do with the freaking out of the atmosphere?
Declan, what's your theorem? Read me your theorem, please. Everybody, let's all write down A equals F over M. So we're on the space shuttle. We got our engines cranked, so the force isn't going to change. What is going to change? Give you a hint. The force isn't going to change. Why would the mass get smaller? What?
It's a shuttle. You're dropping the.
Sadie, finally, loud and proud. What? You're burning rocket fuel. And as you burn rocket fuel, your mass gets smaller and smaller and smaller and smaller. When you divide by a smaller and smaller and smaller and smaller number, what happens to your answer? Gets bigger and bigger and bigger. In fact, it gets so big near the end of the shuttle, they actually had to throttle the engines back. Otherwise, the astronauts would start blacking out. Okay? So you may have watched a launch of the space shuttle on TV in a movie or something, and you may have said, they're leaving the launch platform pretty slowly. That doesn't look like any 5 Gs or 6 Gs. You're right. They're not pulling the G's then. They're pulling the G's about 8 minutes later when their mass is nearly at its minimum and they're still exerting the same thrust. Of course, as M gets smaller, of course, then A has to get bigger if you're using the same rocket engines. I don't want to write a big paragraph. You understand what we just said, though? So, you know what? How about this? As M decreases, A what? My abbrev for decreases and increases are going to be arrow pointing down and arrow pointing up. Nice aha, Sadie. Well done. Oh, how does Newton's second law help explain why a sprinter might want to wear lightweight shoes? Why wouldn't a sprinter want to wear hiking boots? In terms of physics, we can explain this. And I'll give you a hint. It involves Declan's theorem. We're going to name it after you. Declan, what's your theorem? Let's write that down. So you're a sprinter. I'd like my maximum acceleration if I'm a sprinter. Yes? Let's suppose you've lifted weights, you've worked out, you've increased your leg strength so that you've maximized your force. What else can you change in this equation? Lighter shoes? You know what? Same thing. As M decreases, A increases. I'm a little amazed that someone hasn't invented the following product. To me, if I was a materials scientist, This is what I would approach sprinters with. A liquid polymer that they roll onto their feet that would stick for one race. Because the entire upper part of the shoe, that's a waste of mass. The laces, that all that cloth, that's a complete waste of mass. It would be, to me, a polymer that you would like roll on, and then you could also have various tread molds depending on the weather, depending on the track surface, where you would, while it was still liquid, you would step on that tread mold versus that tread mold, and then it would harden, it would stick on the pad of your feet for one race, and at the end of the race, peel it off. If any of you go into materials science and become very good at polymerization and polymers and take that invention, give me 1% of the royalties, please, because to me, that would be the ultimate way to reduce the mass, in my mind. Okay. So Newton's first law, the law of inertia, it's often phrased as objects at rest tend to remain at rest, objects in motion tend to remain in motion, which, Josh, I find confusing. You know what Newton's first is? If you're accelerating, forces are not balanced. If you're not accelerating, forces are balanced. Newton's second law is the equation. F equals what? That was pathetic. F equals what? Kalish never moved his lips, so we're all going to do it again. F equals what? Okay. Newton's third is often phrased, for every action, there is an equal and opposite reaction. You've probably heard that. That's confusing. Here's Mr. Dewick's version. Forces come in pairs. Forces come in what? You know what? We're going to add a word right in here, technically opposite pairs. If you want to write it, go as an equation, the force of object A on object B is the same as the force of object B on object A, but opposite. What would be a good way to show opposite? Will be a really easy, convenient mathematical way to show opposite. Thank you. By the way, Kalish, this also means that a force has to be an interaction between two objects. You have to have two objects for a force to occur. If you had a single object out in outer space, away from any planets, in the middle of nowhere, and it didn't have any engines, no force could occur. It needs a second object. It needs to be an interaction. Okay? Some good examples of Newton's third law. Pause for a second. Sorry for those of you on YouTube, but in class we talked about push-ups. It should be called pushdowns. We said that your arms push down, but if your body accelerates up, what's pushing you up? The ground. And the way I know that is if you try doing a push-up in the air, you don't move, even though your arms are still there. Canoeing, we said on a canoe, you're actually exerting a force backwards. What's pushing you forward, Sadie? The water, absolutely. Forces come in pairs. Helicopters, the rotors push downwards for the helicopter to accelerate up. It's the air that pushes it up. That's why helicopters don't work in a vacuum. And we did the bathroom scale example. How does Newton's third law help explain why it's difficult to walk or drive on ice? Friction is the force that makes us walk and stop and turn. Okay. Put your pencils down, look up. Watch out for that cable there. Another good example of forces come in pairs, Newton's third, firing a high-powered rifle. The rifle applies a force to the bullet. What does the bullet do? It applies the same magnitude force back to the rifle. Right around now, I pause and I say, this is terrible gun safety. Don't ever behave like this around high-powered rifles. This is in a different country that clearly has different gun rules, but this is terrible. Good physics, Broke the window. Actually broke the window. Okay? So, one good example, rifle recoil. Oh, I have some videos that I categorize as bad physics. What do I mean by bad physics? Riley, that's when someone is doing something so dumb that the universe steps in and says, I'm going to teach you a lesson for being dumb. Let me give you an example. Bad
Patrick
physics.
Fisher is gearing up for his big jump. And what's he jumping over? This large pile of loose dirt.
I called my friends and said, hey, I think I might try this once I come by and see if it's at all possible.
Wow, sounds like he's really thought this through.
I don't think he's going to do it.
With friends like these, how could he possibly fail? The amateur daredevil revs up and takes off. Pat is going roughly 60 miles an hour when he hits the dirt with his wheels.
Now let's talk. So let's analyze the physics here. The motorcycle applied a force to the ramp. Forces come in pairs. So what did the ramp do? Shh. Same force in the opposite direction. So the motorcycle just experienced an unbalanced force. It slowed down. Is Patrick attached to the motorcycle? Patrick is demonstrating Newton's first law. He's going in a straight line at a steady speed because the force wasn't applied to him. It was just to the motorcycle. Now, you might think that this is where the universe is stepping in. No. See if you can see where the universe steps in and says, Patrick, you're being stupid. It's when the motorcycle lands on top of him. That's when the universe is stepping in and saying, Patrick, you're being stupid.
Dirt loose was causing my tires to jump and launch me to the handlebars.
So what does Pat think of his momentous jump?
I know not to do something like that ever again. It was just stupid to begin with. It's still stupid now.
But Pat has some words of wisdom for his fellow teenagers.
Think more before you do stuff.
Good advice.
Stupid crook of the month. Bad physics.
Welcome back, everyone. Finally, it's time for our Stupid Crook of the Month. And this time around, you get two stupid crooks for the price of one. Let's go ahead now and take you right to the video, where you can see just how two would-be burglars attempted to literally bust into this establishment. You can see crook number one, the lookout, is handling his assigned task very well, making sure no one is looking, at least so you don't count the surveillance camera.
Crook number two is about to throw a brick or a rock against the window. The rock will apply a force to the window. Forces come in. So what will the window do? Apply the same magnitude force to the rock.
What does he get for being such a quality lookout? Knocked out. The boulder his partner used drills him right in the coconut.
You might think that's where the universe is stepping in. No. The universe has another surprise.
Now that his cohort has completely disabled his partner, it doesn't even check to see if he's okay. He decides to throw another boulder through the glass. Oops! He's a brick sandwich.
I'm going to argue that if you were a Hollywood movie and you had a $5 million budget and you had professional stuntmen, there is no way you could pull that one off. That is the universe stepping in and saying, you're being stupid, bad physics, don't be an idiot.
That's a Looney Tune, like...
The perfect crime was diverted by a powerful one-two window punch, making it the easiest criminals in the history of bad crimes. All right.
Bad physics.
How did they manage that? Didn't even go over some check if his friend was okay. He just bashed himself.
This one is neat, but also a little terrifying. This is the world's smallest manned helicopter. I want you to notice which way the rotors apply force. Oh, by the way, how many propellers do you see? Why? If there was only one, the motor would apply a counterclockwise force to the propeller. Forces come in. The propeller would apply a clockwise force on the motor, and the whole helicopter would spin. In a one-rotor helicopter, the workaround is they have that tail and a small propeller applying a counter-torque. In a two-blade helicopter, the blades spin in opposite directions, so you still have a net force of 0. So you'll notice if you really watch close, the blades are going to spin in opposite directions. From Germany, I think. Of course, you wouldn't want to keep your phone right now. That was silly. Yeah, it's the world's smallest manned helicopter. Want you to notice, so right now he's turning to his right, your left. Which way is the helicopter applying a force to the air? So for him to go to our left, the blades are pushing which way? To the right. So what's pushing him left? Not the blades. The air. Forces come in pairs. The way you think everything moves, almost always, you got to go one step deeper to find what's causing the motion. It's not the initial force, Sarah Ashley, that you think. And that's how he steers. He just tilts those bars in the opposite direction that he wants to go. You can see it's pretty maneuverable. I mean, you're not going to be getting high off the ground or anything, not enough horsepower or wattage, not strong enough engine to do that, but it's kind of a nice little backyard project, kind of a toy. And a nice application of Newton's third. Mr. Duick's law of motion. Newton's first, unloading a truck. So here's a nice example of using Newton's first to unload a vehicle. Where is it, Mr. Duick? Got it here. Oh, there it is. To unload that by hand would be a lot of work, or you can use physics. The truck came to a stop because the friction was applying a force to the tires, but the load had enough inertia, it kept going a little bit. Let's try that again, shall we? This person knows what he's doing, or she's doing. Just fine. How does Newton's third help explain why professional boxers need to wear boxing gloves? Yeah.
Because when you strike someone, the same force being applied to your hand, which is much easier than
I agree. Pause the video. I write an answer, but I don't want to write a paragraph. Oh, how about this? F of fist on face equals negative F face back on fist. Forces come in pairs. Okay. Newton's third. For every action, there is an equal and opposite reaction. That one never really got that. Forces come in opposite pairs. That I can wrap my brain around. Turn the page. If you've ever been standing on SkyTrain or standing on a bus, why do you lurch forward in a bus that suddenly slows? Or why do you lurch backwards when it picks up speed? Or is that what's happening at all? What law applies here? Finley. I think you said it. Yeah, what?
First law.
Newton's first. If you're on SkyTrain and you're moving at a steady speed, you want to keep moving at a steady speed. And so when the train slows, your body wants to keep going at a steady speed and you have to adjust yourself. Or if you're on a bus, the same way. Or in the opposite direction, if you're at rest and the bus or SkyTrain starts, your body wants to remain at rest. A force has to somehow accelerate you forward. That comes through your feet, throws you off balance a little bit. Yeah, I totally agree. So what law applies here? Finley has memorized which law it was. He said Newton's first. And so if you wrote that, I would give you full credit. If you couldn't remember that it was Newton's first, but you could say objects want to continue in a straight line at a steady speed, I would give you full credit. This is why I said yesterday, you don't need to memorize which law is which as long as you know the three laws. But if you want to use the name of that law in your answer, because it's less writing, you can memorize. So since you said Newton's first, we can write, Newton's first. Suddenly we jump to example 2. I need to fix the numbering, but okay. In the collision below, which vehicle experiences the larger force? The truck, the car, or both the same? You know what? We're going to vote. How high you hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. I'm only voting because Mr. Duke will make fun of me if I don't vote. Mr. Duke will make fun of you if you don't vote. Okay? So truck, let's make it a moving van. Big truck. Car, let's make it a little mini Austin. Small car. Okay? So, who says, Mr. Duick, the truck experiences the bigger force because it's bigger. The truck experiences a bigger force. No one. Okay. Duh. The car, because the car gets creamed. It's the car. 1, 2, 3, 4, 5, 6, 7, 8. Who says both the same? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Convince me. Yeah. Which one are you defending? Answer A, B, or C? B? Okay. Convince me. Yeah.
They both experience the same force. Just the truck.
Oh, are you saying forces come in?
Pairs.
Really? What law is that? Newton's what? So because you couldn't remember, I won't let you say Newton's third. You would need to write in your answer, forces come in pairs, and that's what we're all going to write in our answer. Forces come in pairs. Had you known that was Newton's third, I would have accepted you just writing Riley. Newton's third, drop the mic, walk away. I know what you mean. That's why I'm saying you can choose to memorize which law is which. Don't have to. But you need to know what the three laws are. Okay? Before I take your question. So why is it that the car and driver are almost always so much worse off? Oh.
The truck is bigger and the car is smaller. The car experiences less force.
Same force. Doesn't experience less force. Same force.
I mean, it
Declan. I'll give you a hint. In a car accident, it's not the force that does the damage. This would be a good place for Declan's theorem. What was Declan's theorem? Okay. They're going to experience the same force. That's Newton's third. Will they experience the same acceleration? Why not? What? Okay. So, same force. For the truck, big mass, MT at mass truck, small acceleration. For the car, small mass, big acceleration. If I write that, can you figure out what I mean by that? That's short. What does damage in an accident is the acceleration. It's the acceleration. Not how fast you're going. All of you have been going 100 kilometers per hour just fine, thank you very much. But you were able to slow down gradually by taking an off-ramp, by slowing down. Very little acceleration. In fact, so little acceleration, you probably didn't even notice it. You carried on your conversation just fine. You could be going 20 kilometers per hour, and if you come to a stop really quick, you're going to be injured. Why? It's the acceleration. Question. Quick like a bunny. Okay. Actually, can you? I'm almost done. Let me assign the homework, and then I'll turn you loose. So, what's the homework? Number one? Number one says this. Little Nellie Newton wants to be a gymnast, and she hangs from a variety of positions as shown. Since she's not accelerating, the forces must be, I'm looking for a word that starts with letter B. Okay? She weighs 300 newtons. In other words, gravity is pulling down with 300 newtons. Is she accelerating? So forces must be, I'm looking for a word that starts with letter B. How hard must this rope be pulling up with then? So answer A. What about in B? How hard must each rope be pulling up with? See if you can take it the rest of the way. Okay, so number one, I put the answers at the bottom of the page. There's also some questions involving a painter. And 2 and 3 and 4, all of this front page here. Okay, 1, 2, 3, and 4. 5 is good. 6 is good. 7 is good. 8 is good. 9 is good. And 10 is good. So far I've assigned everything, I know. I'm going to give you lots of time to work on this though. And these are good conceptual stuff. Take a look at where it says Newton's third law, number 10. This is meant to be really, really easy, fill in the blank. 10A, head bumps ball, forces come in. Forces come in. Ball bumps head. That's how you'll do all of these. You'll spot what we call the action-reaction pair, the force pair. Okay? So, hand pulls flower, flower pulls hand. Okay? Number 11, a little bit tricky. You're going to be using Declan's theorem, because it's asking you to find an acceleration. Then we get to part 2. It says classify each of these as Newton's first or Newton's third. You know what? You can just write a 1 or a 3. See if I like 1, I like 2, I like 3, 4 is good, 5 is good, 6 is good, 7 is good, 8 is good, 9 is good. And again, just read them, answer 1 or 3. You might even make an argument. Some of them you might say that's an example of Newton's second. F equals what, ma. Newton's. So far, I've assigned everything. I realize it's going to seem like a lot, but they'll go quick. Then we get to this section on Newton's third law. It says, what's the reaction force to the action force? Football player kicks a football 500 newtons up. Football pushes 500 newtons, not up, but down. That's the force that you feel when you kick something. You're feeling that reactive force. Forces come in pairs. Okay? You can skip number 2, the tennis ball question. So now I'm going to start to skip a few. 3 is good. You can skip 4. 5 is good. And I've got the answers attached here to part 2 and part 3. We'll go over some of the answers tomorrow. You have the remainder of class to work on these. Hustle back.